There's something strange moving through our solar system, a mysterious object racing past the sun. We can't see it anymore, but for months, astronomers have been studying it closely. Its official name is 3I Atlas, the third interstellar object ever discovered. Scientists also call it an interstellar comet because it comes from outside our solar system. In just 4 months, nearly 100 scientific papers have been written about this cosmic visitor. Some of the information we have sounds almost unbelievable, but today we'll sift through what's real, what's theory, and what we truly know about 3I Atlas. Right now, 3I Atlas is at its closest point to the Sun, a phase called perihelion. The peak occurs on October 29th, when the comet passes within 210 million kilometers, or 1.4 astronomical units, of the Sun. 1 AU equals the distance between Earth and the Sun, so 3I Atlas never gets closer than Mars's orbit. At perihelion, the comet experiences its highest temperature, causing frozen gases on its surface to vaporize, a process called sublimation, where solids turn directly into gas without becoming liquid. This process creates the glowing coma, a cloud of gas and dust around the nucleus and the tail, which forms as solar wind pushes that material away. Unfortunately, we can't see the comet's full display because the sun's glare blocks our view from Earth. But once it emerges on the other side, we'll resume direct observation. The story of 3I Atlas began in July 2025 when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, detected it. ATLAS is a network of telescopes in Hawaii, Chile, and South Africa, designed to spot moving objects in the night sky, especially those that could approach Earth. At first, the team thought they'd found a new asteroid, but one thing stood out immediately. It was moving far too fast. Objects within our solar system orbit the Sun, bound by its gravity. The closer an object is to the Sun, the faster it must move to stay in orbit. Earth travels at 30 kilometers per second, while Mercury, closer to the Sun, moves at 48 kilometers per second. 3I Atlas was traveling at an incredible 58 kilometers per second, even though it was still out near Jupiter's orbit, about 4.5 AU from the Sun. That velocity meant it wasn't bound by the Sun's gravity at all. Instead, it was on a hyperbolic trajectory, passing through our solar system once before flying back into interstellar space. That's how it earned the designation 3I, the third interstellar object known, following Oumuamua, 1I, in 2017, and 2I Borisov in 2019. 3I Atlas differs from its predecessors in several ways. Size. It's huge. While Oumuamua measured roughly 400 meters and Borisov about 1 kilometer, Atlas could span 5.6 kilometers across. Speed. It's nearly twice as fast as both earlier interstellar objects. Trajectory. It entered our solar system from a completely different angle, moving sideways through the planetary plane instead from above or below. Our solar system forms a flat disk, called the plane of the ecliptic, where most planets orbit. 3I Atlas approached at just a 3-degree tilt from this plane, an almost perfect alignment. That's an incredible coincidence in three-dimensional space, where an object could have come from any direction. So where did it come from? Astronomers traced its path backward and found that 3I Atlas entered from the direction of the Milky Way's galactic core, a dense, bright region filled with stars. Viewed from above, our solar system sits in one of the Milky Way's outer spiral arms. But when we flip the galaxy sideways, we see that most stars and matter lie in a thin disk, with some objects floating above or below it in a region known as the thick disk. Astronomers believe 3I Atlas originated from this thick disk, a quieter region where objects can remain stable for billions of years. That makes 3I Atlas potentially 7.6 billion years old, almost twice the age of Earth. By tracing its motion over 10 million years, scientists calculated that the closest it ever came to another star was 0.3 light-years, 63,000 AU, meaning it spent eons drifting alone before crossing paths with our Sun. Although Atlas officially discovered it in July 2025, 3I Atlas first appeared in May 2025 in images from NASA's Transiting Exoplanet Survey Satellite, TESS, which scans the sky for distant planets. TESS captured the object as it moved through Jupiter's orbit. Astronomers measured the brightness or flux of 3I Atlas to learn what it's made of. As it approached the Sun, its brightness increased five-fold, far more than predicted. This meant the object wasn't an asteroid, but a comet, actively forming a bright coma of gas and dust. Two findings made this even stranger. First was the polarization of light, the direction in which sunlight scattered off the dust. Most comets show positive polarization, but 3I Atlas displayed the most extreme negative polarization ever recorded. This means the light reflected back almost directly, implying unusual surface or dust properties never seen before. Second, the comet developed a visible coma while still beyond Jupiter's orbit, over 5 AU from the Sun. Typical comets remain frozen solid until they reach about 3 to 4 AU, where sunlight is strong enough to vaporize ice water. This told scientists that 3I Atlas wasn't primarily made of water ice. Instead, its coma was dominated by carbon dioxide gas, with a CO2 to water ratio of 8:1, the reverse of what we see in comets from our own solar system. If you've ever seen dry ice, you've seen frozen CO2. It sublimes easily, creating a smoky gas cloud. That's exactly what 3I Atlas was doing, subliming CO2 long before reaching the warmer inner system. As it got closer to the Sun, around 1.5 AU, near Mars's orbit, astronomers observed an explosive increase in water vapor, like a giant fire hose spraying into space. The comet was releasing more water than expected, suggesting internal layers of frozen water beneath its CO2-rich surface. Even stranger, the comet's coma contained nickel but no iron, an imbalance rarely seen, since both metals usually form together inside dying stars. The missing iron puzzled astronomers. As the comet approached the Sun, iron did eventually appear, restoring a more normal nickel-to-iron ratio. It's possible that the CO2 jets initially dragged out lighter nickel atoms first, before enough heat liberated the heavier iron. Then came another surprise. Its tail was pointing the wrong way. Normally, solar wind pushes dust and gas away from the Sun, forming a tail that trails behind. But early images of 3I Atlas showed a sun-facing tail. Scientists think that's because at such a great distance, the solar wind wasn't yet strong enough to push material away. Instead, gas built up on the sunlit side, giving the illusion of a reversed tail. By September, as Atlas neared Mars' orbit, it developed a short, fan-shaped tail pointing away from the Sun, the expected orientation. Not all comets grow long, sweeping tails. It depends on composition and proximity. For example, the famous comet Hale-Bopp in 1997 had a spectacular tail because it came much closer to the Sun, at about 0.9 AU. On October 3, 2025, 3I Atlas made its closest pass to any planet, just 0.19 AU from Mars. Luckily, Mars has several cameras both on the surface and in orbit. NASA's Perseverance rover managed to capture faint streaks of the comet in the night sky by stacking multiple 30-second exposures. Meanwhile, the ExoMars orbiter provided a clearer image, though still too distant to distinguish the nucleus from the coma. The best opportunity for a detailed photo would come from NASA's Mars Reconnaissance Orbiter, equipped with a high-resolution telescope. However, due to a U.S. government shutdown at the time, it's unclear whether that observation was ever made or released. For now, the sun's glare hides 3I Atlas from Earth-based telescopes. It will remain invisible until early December when it reemerges. On December 19th, it will pass 1 AU from Earth's orbit, giving scientists a brief chance to observe how solar heat and radiation have changed its structure and composition. After that, 3I Atlas will continue outward, cooling and slowing as it leaves the inner solar system. But its journey isn't over yet. It still has one close encounter left. On March 16, 2026, the comet will pass within 0.36 AU of Jupiter. NASA's Juno probe, orbiting the gas giant, will likely capture the final images before the object disappears forever into the darkness of interstellar space. By then, 3I Atlas will be growing dimmer and less active, but it will carry new information, altered by its brush with our sun. Its chemical layers, gases, and dust could tell us not only where it came from, but also how it changed during its brief visit through our solar system. Why 3I Atlas matters. Each interstellar visitor offers a glimpse into other planetary systems, snapshots of materials formed around distant stars billions of years ago. The differences between 3I Atlas, Borisov, and Oumuamua remind us that what we consider normal here may be unusual elsewhere. The extreme negative polarization, the early CO2 activity, the inverted metal ratio, all of these suggest that other star systems form comets with different compositions, temperatures, and histories. Studying 3I Atlas helps us understand not only how our solar system compares to others, but also how material travels across the galaxy. Though we may never trace its exact birthplace, 3I Atlas has already expanded our understanding of what's possible. It shows that even in the vast emptiness between stars, ancient travelers still drift through space, each one carrying a story billions of years in the making. When it vanishes beyond Jupiter's orbit and fades into the void, we'll still be analyzing its data for decades to come. Every question it raises brings us one step closer to understanding how worlds are born, how they evolve, and how our tiny corner of the galaxy fits into the grand, mysterious dance of the universe.